Hello and welcome to YMT 215 Logic Circuits. We are still discussing Chapter 1. This is the second part of the introductory concepts. We are just at the beginning. We discussed two topics before in the first video. Today we will discuss another two topics. We will discuss basic logic functions, combinational and sequential logic functions. So they are essential, and we will see why we have actually a separate topic for logic functions and what they are. In brief, in order for us to understand logic functions, we need to go back to the basic element of logic functions. Actually, we have something we call preposition, and this preposition, even in terms of the language itself, we have a preposition that can be true or false, right or wrong. Declarative statement. So this declarative statement is a statement that tells something that can be true or false depending on certain conditions. So any proposition or any declarative statement must be evaluated to one of two states. Now we say one of two states. Let's just revise what we said last week about two levels. So two statements, two levels, so high, low. In this case, we say true and false. So do we have any relationship here? For sure. So surely we have a relationship, a direct relationship, and this relationship states that declarative statements or prepositions can be represented by simply basic logic functions, high and low, or 1 and 0. So we can represent true by 1 and false by 0. So the outcomes of the evaluation of any declarative statement can be represented by true or false, high or low, 1 or 0. We get back to digital. This is the relationship, the direct relationship, the reflection of the combination between logic, the basic logic sense, declarative statements, and the binary digit or the bit. Okay, so now we got the idea: true, false, high, low, or 1 and 0. So how can we compose logic circuits based on that, or digital circuits based on that? We need to go back to a concept called actually Boolean algebra. We will come to it in a while, but before I go to Boolean algebra, let's just take a simple example. Let's just consider a very basic or elementary propositional statement or declarative statement. Something like this tells you a possible outcome of a statement that could be true or false. So the light is on. The light is on. When I say the light is on, my statement or this proposition can be true or it can be also false. Depending on what? So depending on the condition, whether it is really on or off, or whether we have electricity or not, or whether the bulb itself is not spoiled, or not spoiled, if it is functioning or not functioning. So these conditions may take us to some other declarative statements. Now look at this. If we want to a little bit elaborate this statement, the light is on. We can put some condition. The bulb is not burned out and the switch is on. So now we have electricity. The electricity is on. There is no problem there is no blackout. So we have electricity. The switch is on. The bulb is not burned out. It's not spoiled. It's functioning. So we assume that the light is on. Well, we can compose a bigger, or actually combinational statement from these prepositions. The light is on only if the bulb is not burned out and the switch is on. This is a bit bigger statement with some conditions, with if statement. We will study their composition later on, but the basic idea is this is a preposition which relies on other conditions. So one basic preposition may need certain other declarative statements for it to be true or to be false, depending on the outcome that we are looking for. Now, I said earlier, all basic logic functions rely on something we call Boolean algebra. Boolean algebra is one type of mathematics, or one stream from mathematics developed or invented by George Boole. It is actually about formulating symbolic representations of these declarative statements. Now look at this statement. It's a bit long, right? It's long. If we add few other sentences to it, few other conditions or assertions, a few other prepositions, then we will have few more lines. And usually such a representation is not recommended when we deal with a machine. With a machine we need symbols. We need actually simpler things like just X and Y that do not take much of a space, and they are easier in representation. And for that reason, this scientist developed the transformation, or actually the formulation of symbolic representation of assertions or prepositional statements, and create one stream of mathematics, what we call Boolean algebra. And this is actually the base of the digital machine that we have. Any digital machine, your computer, your phone, a tablet, whatever that has the electronic circuit in it, okay? Now, what is actually the base of Boolean algebra in designing circuits or digital circuits here when we say? We don't refer to electronic circuits that are pure analog. We need actually to refer to digital. So when we speak about electronic circuits in our course, we speak about, or we refer, or actually we mean digital circuits. So we have three main gates, logic gates. So these logic gates are actually the foundation of everything else. So whatever you think which is extremely complicated, like the machine that we are using, the computers that we are using, are composed somehow from these three gates. But of course the combination here of different functionalities have not only one gate or two, there are millions of these gates, but the foundation actually rely on these three. So these logic gates are actually AND, OR, and NOT, and we will explain their functionalities one by one, and what actually they refer to, and what kind of input they need, and what kind of output they reproduce. Now, for NOT, it's simply an inverter. Inverter means what? If you supply high, the output will be low. So if the input is high, now what we are expecting here is low. There is no other choice. It just inverts it. If it is low, there is high. So in digital circuits, we said again, we have two levels, two states, high and low, or 1 and 0. So if I supply 1 here, the output will be 0. It's the inversion. The inversion means what? We have 1 and 0. There is no other. So if the input is 0, it will be inverted to 1, and that's it. For AND, by the way, before I go to AND, for NOT, we can only have one input. Why? Because we are just inverting the input. We cannot have two. There is no combination here in this case. We just need to have one input, and this input will be inverted, whatever it is. But for AND, we can have as many inputs as possible. It doesn't matter because it's combinational in this case, and receives as many inputs as required. And the output relies on the states of these inputs. AND gate is actually a unique gate. It's like a connection in series in electric circuits. You studied this in physics, I believe, or maybe you are studying it now. I'm not sure. What it means? It means all the inputs must be high in order for the output to be high. If any of the inputs is low, or all of them are low, then the output is low. So the idea is like this. If we input anything other than high, or anything other than 1 on any of these inputs, then the output is surely 0. And if all these inputs are high, then in that case we will have just high output. Or is also having a number of inputs, so it allows, the combination of a number of inputs, and in that case what we can do is we can have just one output, of course, here for these gates, only one output, all of them, but different inputs, and these inputs will allow us to go for combination. So for OR is unlike AND. If any of the inputs is high, or all of them are high, then the output is high. Otherwise, if all of them are low, then the output is low. Okay, so for the time being, the idea is a bit maybe not quite clear. Don't worry, we will take in the next chapter truth table, and the idea will be revised and refreshed in your brain. So this is just the basic concept. I explained about the inverter, NOT gate, and I explained about AND and OR, and their functionality and how they work, actually their states. We will take truth table in the next chapter and we'll explain further about them and how we use them. But for the time being, it's enough for you to understand what I said, how their states work. For the AND gate, it works if all of them are high, it produces high, otherwise it is low. For OR gate, if any of them is high, it produces high. Otherwise, if all of them are low, then it produces low. Okay. Now we may think about a bit more complicated representation of gates. When we arrange them together, we have some certain electronic circuits or digital circuits. In this case, we call them combinational and sequential logic functions. So what we can use is the three gates to create a bit more advanced logic functionalities. What kind of logic functionalities that we are looking for? Now our machine doesn't rely on AND or NOT only. No, it needs actually an arrangement of AND, OR, and NOT to produce comparison, maybe arithmetic, addition, subtraction, division, multiplication, code conversion. We have different types of code conversion. We speak about it: encoding, decoding, data selection, and counting, storage, and so on. So whatever we stated from those, your machine is doing. You have a storage in your machine. Think about your RAM. It's a storage, temporary, yes, but it's a storage. Think about the ROM of your computer. It's also storage. It's created from solid state, or what we refer to in this case logic circuits, or chip, actually a chip, and this chip is composed of a logic or digital circuit. Counting also, encoding, decoding, we will take them in their time. On time we will take those, but these are not composed of only one or AND. No, we need to have actually a number of. Okay, so the arrangement of these logic circuits will allow us to have combinational or sequential actually logic functions. And we will just give some examples now. You may say, okay, how do I know how to design them? You don't have to. Now it's not actually the time for that, but you need to have an idea about what we can do with these gates. And soon enough, after we start taking a little bit advanced chapters, we'll be able to design them in actually an easy and convenient way. Think about the comparison. This is one of the functionalities that we have in our machine. It's a digital circuit also, or a digital functionality. Comparator, imagine we have two inputs for two numbers we need to compare. They could be also letters, but for the time being we think about numbers. We need to compare them. If they are equal, not equal, if they are not equal, which one is greater and which one is less. This is a comparator. So look at this representation. This is a comparator. We have two inputs, A and B. And if they are equal, we have one output indicates that they are equal. How do I know that this one is indicating equal? This one will be set high and these two will be set low if these two quantities are equal. Otherwise, let's say A is greater than B. This one will be high and this one will be low and this one will be low. So the output will be activated high depending on the state. If A is equal to B, this one will be activated high. If A is less than B, then this one will be activated and these two will be deactivated. Activated means high, so this one will be 1 or high, and these two will be 0 or low. So 0 will be here, 0 will be here, and the same goes in other cases. If A is greater, this one is high, low, low, and so on. So which one would be active is determined by the state, the real state here. Which one is greater, or if they are not greater, equal, will be activated. All right. Addition. We have arithmetic functions. We said addition, subtraction, division, and multiplication. These are actually composed from logic gates, but in a specific representation. And what we have, actually our computer doesn't exactly understand add this number to this number. It's not like the human being. They are working on such machines. They understand human words or instructions to do the process. But the machines that we are using, the computer that we use, do not exactly understand the instructions that we give them this way. They understand instructions based on their own design. What does it mean? If you want to add, let's say, 1 plus 1, it doesn't understand it this way. It understands it by a certain representation of logic circuits. So if you are adding 1 plus 1, then you need a circuit similar to this. You need to have two binary numbers, A and B, and you need to have carry in. And the output will be the summation from one side and the carry out, like the basic mathematics we learned at schools, and this is exactly the case. So if you think about the binary code for 3 here and the binary code for 9, and we have the binary code for whatever carry in, if we don't have carry in, that means 0, then there will be the binary code for whatever the result here, 3 plus 9, that's 12. And in that case, we will have 2, and we will have also carry out 1, 2, and 1 carried. So we will have the carry out. We drop the carry in front, the carry in front of 2 here in this case, and we will have 12 as the outcome. This is just in decimal. Usually we don't do that in decimal. We do it in, in binary. But until we reach to the adders, after a few chapters, you don't have to worry about how it is done. I'm just giving you an example about the arithmetic. So we can compose the circuit by AND and OR gates. It's possible. And this is the way it is designed. Do I bring such a thing on the exam? No, I don't do that. I will bring it when we study it. When we study such design, I'll bring you questions about it. It's just an example. How about the subtraction? The subtraction is also a vital arithmetic operation, and also our computer doesn't understand it like 3 minus 4, let's say, or 3 minus 2, or 5 minus whatever 2. In that case, no, we need to have, you can say, an application for the subtraction to be achieved. And in computing, what we do, we use actually adders to achieve the process of subtraction. How do we do that? Later on we'll explain about it. We will have design for subtractors, okay? But in brief, instead of having here carry out, we will have, and carry in, we will have borrow in and borrow out. So these are actually the differences. We will have borrow in and borrow out, and we will have the result of the subtraction and the two numbers to be subtracted. Multiplication in computing is not exactly done the way we human beings do. Rather, it goes to the elementary way. Maybe you studied this in school. Multiplication actually is represented by summing up a number of times. So let's say if you see 3 times 10, so it is summing up 10 3 times, right? 3 times 10, that's 30, or summing 10 3 times, 10 plus 10 plus 10. That's one way to do it in computer. There is also another way of shifting the number to right side and then, to left side and then adding. So we shift and add, and that's possible, and we will teach you that method later on when we reach to the design of the multiplier in real sense, not just an example now of the arithmetic functionality. For division, it is the opposite way of multiplication. It's actually subtraction of the number certain times or repetitive times. It's actually the inversion of multiplication, but what we do it in this case, is we shift the number to right side and we add, shift and add, shift and add. And in this case, what we are aiming to get is something we call the quotient and the remainder. Why? Because we expect to have a result with some decimal point. And in that case, we may use some adder, it's addition again, with some conjunction with some other circuits, some other gates. Okay, so it's actually a series of subtractions. Again, we said subtractions, and comparison, subtraction and comparison, and shifts. So that's the idea. Code conversion in digital electronics, we have a lot of codes to be converted from one to another. You may say, okay, why do we need to have different types of codes? What's the reason for having different codes? Actually, we have different representations based on the application that we have. So think about, let's say we speak about decimal numbers. Our computers do not exactly understand decimal numbers, they convert them to digits. So we need to have a converter here. This converter could be binary coded decimal. So we code the decimal numbers to binary code. And we have another code which is simpler than binary codes, or the BCD. We call it gray code. And we will explain later on why, when we study codes, why gray code is simpler and actually more robust to many applications. So we need to have converters between those. All right. And what actually codes a number from one state to another, we call it encoder. It converts a state to another state. Think about converting a decimal number to a digit. That's an encoder. Think about converting an alphabet, so alphabetic character, into a code. That's also a converter. And so on. There are so many examples. Look at this. This is a very common example. If you have some keypad for calculator or a touch, whatever, screen for these digits, you will have an encoder. It will activate the code for whichever number you touch or operation you touch here, or maybe it could be the period, based on these inputs. So the inputs will convert when the input will be activated high. If you press 9, this one will be activated, the line will be activated, 9 will be activated, and the output will be coding 9, and so on. How it does it, later on we will study that. It's just an example how encoders are actually composed or created and how they operate. Now, we said about encoders, transferring one state of data to another state, usually non-digital data to digital data, maybe some digital data to another, from one form to another form. We need to have a proper way for decoding. Decoding means converting to the original state, getting back the data to original state. So imagine we have a binary number that represents a decimal number. So how can we get it back to its decimal state? We need to have a decoder. So it decodes the digital form or the binary form to the decimal form. For this case, in this case, if we speak about decoding of digits to decimal form, we speak about actually something we call readout. One of the very popular decoding functions is actually the readout of binary codes into appropriate decimal digit. The readout actually is a decoder for an input, digital input of course. We have a digital code and it actually represents the output based on decimal. So if we say 4-bit, we expect something up to 9 in this case. So we can count from 0 to 9. These are the decimal numbers that we know from 0 to 9. Then we repeat 1 0, that's 10, right? So in that case, we may have something like this, a binary code, and then we represent the output based on this representation. We have 7 segment display, segment Y. We have, if you count here, 1, 2, 3, here 1, 2, 3, and this is 1. So 3 plus 1, these are 7 segment. So we have 7 segment for the display, and they represent actually the 4-bit binary code. We will explain about those later on and how it is designed, but it's just the decoding functionality of a decimal input that binary input that codes actually decimal numbers. Okay. Data selection. For data selection, we have actually two main applications of digital circuits. We have a multiplexer and the opposite of multiplexer, or the inverter of multiplexer, the demultiplexer. Multiplexer is actually explained in a simple way by representing a switch, or having a switch that takes inputs from different sources onto one line. So we have different inputs, more than one, different inputs. We take them, all of them based on time or frequency. That we have different representation of multiplexers, but you don't have to go to that. Let's think about time only. So we assign time for the first input, another time for the second input, another time for the third input, and we take all the inputs onto one line. So we have several inputs, we switch them to one line, or just we pass them on transmission of one line. So this is the idea of multiplexer. We usually refer to multiplexer in short by mux. Okay, now look at this. This explains it. So we have 3. It could be more than 3. It's just an application. We assign a time delta t1, delta t2, delta t3 for each input to take it onto one line. This is one line here. And then we transfer them. Okay. Once we need to represent them to their original state, we need to use demultiplexer. For the demultiplexer, it's actually a converter of the multiplexer. It does the opposite way. It redistributes these inputs assigned to the line, or actually transmitted on the line here, the transmission line. We redistribute them based on their timing, delta t1, delta t2, delta t3. How it is done, you don't have to think about it now, just understand that there is something we call multiplexing and demultiplexing based on this process, taking from different sources onto one line, redistributing from one line to different outputs based on certain timing manifest. Okay. Demultiplexer, or demux, I explained about it, is actually the reversal of the process of mux. It does exact reversal. We take from one line, we distribute to several output lines based on the timing we assigned here, delta t1 and 2 and 3. Okay. Storage functionality. We explained earlier that we have something we call storage in logic circuits. It's one part of the combinations of logic, or the combinational logic circuit. Could be also sequential, depends on your application. But we have different storages that we use in our computing system. We have short and long term. You studied this in Introduction to Computer Science. So for those who maybe forgot about the types of memories or storages that we have in our computer, we have the short and long term. Short term, think about the RAM. As long as your PC is on, the RAM holds the data for that period. It may erase them for some application, but not fully. But if you switch off your PC, whatever in the RAM will be flushed, and most likely you cannot get it by simple ways. You need to go to experts to try to extract whatever remains on it. But usually it just flushes it and it goes. For long-term memory, it's like your hard disk. When you store something on your hard disk, unless you delete it, by itself will not be deleted unless there is a problem or some malfunction in your own PC. Okay, so how can we create such memories? Well, for the semiconductor, the solid state we use digital circuits or logic circuits, but for the long term, in this case, like the big memory type or storage type, usually we use the magnetic disk, although we have the SSD now. It's available, the solid state actually disk. But for the time being, think about the magnetic disk. I think you remember it from Introduction to Computer Science. It's not exactly solid state. It's actually a mechanical. It has a rotating part with magnetic disks stacked on top of each other, and we have some reader that moves in between. That's why it's a bit slow. We have also the magnetic tape. It's bigger than the hard disk. Usually those magnetic disks are used for hard disks, the old version, other than SSDs. But for the magnetic tapes, usually they are much bigger. They use for supercomputers or maybe server side or whatever. Semiconductor, think about the flash memory. All of you guys are using the flash memory, I think, or for some period in your life you've used it. That's a semiconductor. There are also other types of semiconductor. We have something we call registers. You remember, I'm sure you remember something we call registers in computer memories. They are actually a combination of flip-flops. What are these flip-flops? Flip-flops by themselves have their own chapter, but they are the simplest and the smallest memory in digital circuits. They are actually a combination of gates that represent a storage capability of storing only one bit at a time. So there is a connection, certain connection of gates. We will study them, how we connect these gates, and they form a circuit that's able to store one bit at a time, just one bit, either high or low, okay, based on the output that it produces. But if we cascade, if we put stages next to each other, we will have a register from flip-flops. So these flip-flops, we can cascade them. Cascading means what? Setting up a stage, we connect it to next stage, we connect it to next stage. So the first stage can hold a bit, second stage another bit, third stage another bit. If we put 8, then we will have 8 bits. If we cascade 8, so we will have 8 bits, we will have 8-bit register. So these registers, by themselves, they have their own types. We will speak about them in a while. This is just an example. The design is not now. Later on, we will explain the concept of flip-flops and how we can create registers from them. And we have also the optical discs. You're familiar with those CDs, DVDs, Blu-rays. All these are optical. They are not exactly based on the semiconductors. Semiconductors here, we refer to the solid state, things that store bits by ones and zeros. In optical discs, the data is not exactly stored by 1 and 0. They are stored by there is no. What we refer to here by 1 and 0 is exactly the state of the memory. Why we actually use in optical discs some mechanism for laser diode that actually burns the data if it is available. It creates something like a pitch on a track, a concentric track of the disk. It burns it, that means there is memory, or it leaves it out, that means there is no. And that's why it's not exactly digital, but it can be converted to digital. So it's coincided with actually the state of 1 and 0 or low and high, but it's not semiconductor. This is what I try to explain. It's an optical way of doing it. However, it goes along with the concept of 1 and 0. Okay, I explained about the flip-flop. One thing I didn't say, which is actually bistable. Flip-flop is a bistable device. Bistable device means what? It has two states. So what am I trying to say? Two states, that means two outputs. So we will have for any flip-flop two outputs. One of them is the opposite of the other. So if you have at one side of the output 1, then the other will have its inversion, 0. Or if it is high, the other side will be low. That's why we call it bistable in this case. Two states, two stable states, and in this case they are opposite to one another. Now, opposite to one another, well, we will not benefit too much from this idea. Why? Because one of them it's the inversion of other, but when we cascade them, yes, we benefit from this state. Cascading them, creating a more complicated form of storage or maybe counter and so on. Okay. I explained about the simplest memory type. Register, we said that we can form a register by combining flip-flops, cascading usually flip-flops. Actually, not all the time cascading. Why? Because cascading in this case will compose only one type of register. We may have other design other than cascading, and in that case, we will have different type of register. One very popular type of registers, we call them shift registers, and I will show you why and what we mean by shift. Now look at this. This is a 4-bit register. Initially, it's fully empty. Zeros here we refer to a state of empty. It has no data in. It's not storing anything. If you want to store things on it, you will go 1 bit at a time by shifting what's inside and placing something from the input. Now, if you remember last class, we explained about a clock cycle that actually synchronizes the process. So for each of these bits, we need a clock cycle that gets it in. So each cycle from a clock allows us to get 1 bit in, 1 bit in, 1 bit in, until we get all of them in. If you further apply clock cycles, these will be excluded. And if you don't have any input in, then back again we will take all zeros. But this is the idea of a shift register. You don't have to worry about design now. How it works. Just understand as an example how a shift register works is by shifting the bits based on synchronized clock, and it is designed from flip-flops. Okay. This is a parallel register. Parallel register is another type of flip-flops combination, and it stores the bits all at once by one clock cycle. How it is done and how it is designed, not now. We will study it in its time. So instead of shifting 1 bit at a time with each clock cycle, we will have just one clock cycle, and that will get us all the bits in. Okay. Semiconductor, we explained about semiconductor memories, the solid state. We may think about either the two actually most popular, the ROM, read-only memory, that stores the information or the digital data permanently. And if you want to remove whatever available in ROM, it's not that much easy. Even if it is erasable, you need to have some laboratory functionality to even erase the things on the ROM and reprogram it. Not all ROMs are reprogrammable. We will study them. But if it is just ROM by itself, not programmable or not erasable, you will not be able to erase. If you erase it, that means the ROM itself is spoiled, finished, you cannot use it. And that's why usually the BIOS of our computer is actually stored on ROM. Why not to lose them? Otherwise your computer will not start. So it's like the basic programming functionality that allows our computer to load and gets your operating system on. Okay, the random access memory, RAM, unlike ROM, it's actually temporary memory that stores the data for a certain period based on the need of the computer, or once you terminate the operational process and turn off your computer, whatever in the RAM will be actually flushed, and most likely you will not be able to get it back in simple ways. I repeat always in simple ways. Why? Because maybe after you study like advanced courses about maybe forensic or things related to extraction of digital evidence, you will learn that it is possible to extract things from RAM even after switching off the computer. But these methods are actually extremely advanced, and they are not as simple as we think about them, but they are possible. That's why I say, for you to get the information available in RAM after switching off the computer, you have to go to experts. And those who have certain packages of software that allow you to do so, and you will not get full information that were available that was available on the RAM right before switching off. But yet, I keep telling it is possible. So if I say it's not possible, it's gone totally for good. No, that's not the case. Okay. Magnetic memory, I explain about it like the hard disk, the magnetic tape. Usually they are bulky, big, they rotate, they make noise. They are not that much flexible. Okay. So they are slower than the SSD or semiconductor. They have their own advantages and disadvantages actually, but they are a type of memory which we are still using. Okay, if you compare the hard disk composed of magnetic memory to the hard disk created from solid state or the semiconductor, it's much cheaper, especially in the peak of the strike of prices now. If you compare those, well, you may go for hard disk. You say, okay, I'll hold my patience a little bit for the hard disk to load, overpaying like maybe, I'm not sure, a couple of $100 to buy another disk that's faster. So it's actually price versus speed in this case. Optical memory, explain about it. I don't want to get back to it. I explained about the concept. So I said about it earlier. I don't want to explain about it again. Counting, one of the functionalities that we also have from logic circuits. Counting is what? Actually, it's like the basic concept we have in our life. It's counting things, 1, 2, 3, but it is not done that way. In computer, it's done based on digits. And for that, we need to have a circuit, digital circuit or logic circuit that counts for us based on digital codes representing 1, 2, 3, etc. Okay, how do we do it? We need to have a memory that holds the count, the current count, so that we move to the next count. So let's say we are at 1, we need to move to 2. So we need to hold the current state in order for us to move to 2. Once we move to 2, we need to hold 2 so that we can move to 3, and so on. So storage, so we said something that holds for us, that's a storage, flip-flop or flip-flops, depending on the number that we want to hold. So 1 could be just 1 bit, but 2, that's not 1 bit, it's 2 bits in this case, and we will explain about that later on. 2 bits means what? Because this is decimal. We'll explain about the numbering systems in the next chapter, not now. Well, this is the idea. Now, this is a whole example. Do not be shocked or puzzled. You don't have to design anything yet here. You don't have to know about all the details. But what I want you to know, this is a practical example of a counter in the computer. Let's say we need to fill up 50 tablets of those. Let's say these are the medication pills or tablets. We need to fill in these bowls 50 of them. So we need to decode 50 from a counter. So we need a counter that counts from 1 until 50, and once it reaches 50, then we set it up to 0, count again from 0, move the bottle. Okay, so this is the idea. It's widely available, especially in industry, so we don't count by, human power. That will not produce us actually an efficient way. Usually this is done in terms of, automated process with robotics. And that's why we need to have a counter with some decoding functionality, so that when the counter counts to 50, we get it back to 0, we erase whatever available, get back and count, move the bottle, and so on. This is actually the end of our session. We will have the third and last part of this chapter. I'll upload it as soon as I can. Until then, have a good time. Goodbye.